Okay, what is the deal with geometric optics? That pen is out. So the idea with geometric optics is just that. We're going to talk about optical elements, and the important components of the optical elements is the geometry of the setup. Okay? And this entire chapter can broadly be categorized under one following statement. Light is a ray. All right, we learned about light a little bit in the last chapter when we talked about electromagnetic waves. We said that electric fields and magnetic fields can oscillate together and they can propagate along as an electromagnetic wave. Okay? That is what we call light. Specifically, light refers to sort of the visible portion of the spectrum, but a lot of times you hear physicists refer to the entire electromagnetic spectrum as light. Okay? So electromagnetic spectrum is pretty big. You've got X-rays at the very short wavelength scales, you've got radio waves at the long wavelength scales, and somewhere in the middle you have the visible spectrum. You got the Roy G. Biv, right? The red, the yellows, the greens, the blues, the indigos, the violets. So light is a ray. What does that mean? It means it travels in a straight line. Okay, now there's a caveat there, which is the following: in free space. Pretty soon we're going to talk about what happens when it meets up with glass or water, and then you can see that the ray will actually bend. But in free space, light travels in a straight line. It's a ray. So when you think about a star, here's a distant star. Okay, what is that star doing? Well, it's spitting out electromagnetic radiation in all these different directions. And each little bundle acts like a ray. And so if you're sitting down here on Earth and you're looking up at that star, there is a ray that came directly to you. And it's kind of weird to think about, but that little photon, that bundle of energy that left the star however many millions of years ago, traveled in a straight line all the way across free space, all the way to your eyeball. You detected it, and it was gone. Okay? So that was the source of the ray. This was the sink of the ray. Started there, ended there, traveled in a straight line. The fact that it travels in a straight line lets you determine exactly where that star is. Now, it gets a little more complicated once we get to general relativity, but for now, just consider those rays moving really in a straight line. You look up, came from there, that must be where the star is. All right, what about when light rays bounce off of stuff? So let's say that that light ray comes at us, but it's not going to hit your eye. It's going to bounce off of a mirror. So we have a mirror right here. Here's a mirror. Can you guys see that? Probably if I look just like that, you can maybe see my reflection. Can you see my reflection? It's a really dirty mirror. Okay? That's a mirror. What is a mirror? A mirror is very simple. It is a coating of aluminum or silver on glass. Okay, there is a glass substrate, and on that glass substrate you provide a little bit of aluminum or silver. If you have a lot of money, you can buy gold mirrors, right? You can put gold foil down onto a glass substrate. And so it looks like this. Here is our glass. And then right on top, there is a very thin coat of metal. Okay, and it doesn't have to be very thick at all. The metal is what does the reflection. So when a light ray comes in, here comes our light ray. It hits the mirror and it bounces off. Okay? Why does that happen? Why does light bounce off of this mirror? And the combined two things here, the glass and the metal, is what constitute the mirror. Why does that happen? It happens because we know that light is made up of electric fields and magnetic fields. And when those electromagnetic fields hit the metal, the little charges in the metal start to vibrate. And they vibrate at exactly the same frequency as that light ray that was coming in, and it re-radiates that stuff out into another ray at the same frequency. Okay? This is why you have to have metal there. If you have an insulator, like a piece of wood, it doesn't reflect the light ray. And that's because those little charges in the wood can't move quite as easily as the charges in the metal. So the metal is, in fact, what does the reflection. Metal causes that reflection to happen. What is the purpose of the glass? Let me ask you guys. Chime in on the chat room and tell me what the purpose of the glass substrate is. Right answer. The purpose of the glass substrate is purely to keep the metal flat. So if I think about a piece of metal like this, it can be kind of flimsy, right? It's easy to bend. And if I bend this, you can see the reflection change shape, okay? Think about when you open a brand new can of aluminum foil, right? It comes out and it looks like this. And it doesn't make a very good reflector. But if you pull it out very slowly and lay it on the table, then it's flat. And so that's it. The whole purpose of the glass is to keep it flat. There's an additional purpose, which is to keep it from oxidizing. So typically when you look in the bathroom mirror, there is metal coated on glass, but the very front side is glass. Then there's metal behind it, and then there's some other sort of protective backing on it. The glass is really just there to keep it flat and to keep it from oxidizing. The back substrate just keeps it from oxidizing, which is the law of reflection. And we sort of alluded to this in our first picture, which is the following. Let's say we have a mirror. Okay, we know that a mirror is made up of shiny metal. And let's say that we have a ray coming in at some particular angle. And when we draw these angles, we always draw it relative to the surface normal. That incident angle, we call it theta I. Now, going out the other side, we of course have a reflection. And if this is a nice flat metal surface, then that reflection is at theta R, and the law of reflection says the following. Theta I is equal to theta R. Incident equals reflected. Remember, they're always relative to that surface normal. Okay, so in the case of the mirror that we just talked about, we said, where is the image? Using this law now, we have to think about how do you form an image in a mirror? So let's draw the following picture. We've got a metal mirror that we're going to make vertical. Let's put in what we call the optic axis, and let's put an object right here. What do the rays from that object do? Well, first of all, how are those rays generated at all? Light illuminates the object just like light from these lamps is illuminating me. Every single point of me is reflecting rays in all directions. So if this is an object, if this is an arrowhead object, light that is hitting the tip will go off in all directions. Light that is hitting the base will go off in all directions. Just like when you look at this image of me, light from my cheek is different than light from my nose or my hair, and yet those rays are going off in all directions. You intercept a few of them with your eyeball. So let's think about where the rays will be going from here. Okay? Light comes in, bounces off. We don't have to worry about the light coming in. What we have to worry about is the light bouncing off. So one ray will do this. It will bounce off of the mirror and come back. And if I continue with a dashed line, that is where that ray appears to be coming from. Now, if I think about an observer, here's my observer, then there will be a ray from the tip of this object that comes up and bounces off and goes into the eyeball. And now if I take a dashed line and continue, the point where those two dashed lines intersect each other is where the image is located. So that object has an image that is right here. Okay, and so everybody got it right. The image is equidistant from the mirror on the other side. And you know this already, right? When you stand in front of a mirror, you see an image of yourself on the other side of the mirror, the exact same distance away. If you're standing 2 feet away from the mirror, it looks like you have an image that's 2 feet on the other side of the mirror. If you back up further, your image gets further and further away. Okay? As you get closer, it comes closer in. So everybody got that one right. Their intuition was correct that it was indeed answer B on that clicker question. And the way you see that is this idea of the law of reflection. If this ray comes in at this angle, it's going to go off at the exact same angle relative to the normal. And now you just have to follow those lines back. It's kind of weird, but when you see something, you see what you think is where those rays are coming from. Right? If the mirror wasn't there, you wouldn't see an image over there. Okay? Putting the mirror there means that it looks like those rays are coming from there. Let's say we're standing in front of the wall mirror, and the wall mirror is not half your height. It is maybe 1/4 of your height. Okay, so here's the wall mirror, and here you are. Okay, and let's move this mirror up just a little bit so it's even with the head of the person. Okay, and the question is the following. If you are height h, and this thing is h over 4, how far back do you have to stand to see your shoes? Okay, namely, you're standing next to this mirror and you can't quite see your shoes. Okay, how far back do you have to go in order to see your shoes? And this thing is wall mounted. Okay, it's flat. This is our wall. It's a flat mirror, it's perfectly vertical, and you're just going to walk back on a level ground. How far back do you have to go to see your shoes? Discussions out there. A lot of people said, oh, it's got to be 2H. Some people said, well, it's 1/4 the size of a mirror, so it's got to be 4H. Let's see if we can think about how this is going to work. What we said was that rays that bounce off a mirror bounce off the exact same angle they came in at. So if we think about the bottom of this mirror and a ray going from the bottom of the mirror to the person's eye, where did it come from? It had to come from about there. Okay. Incoming angle has to equal reflected angle. All right, so at this distance right now, you can see maybe your midsection, right, your belly button. But now let's take this person and let's move them far away and see what they can see. Okay, we'll extend our floor a little bit. And now that person is right here. The light ray that came to their eye had to come at an exact same angle. Okay. Can they see their shoes? No, they see their belly button again. As the person steps back, those rays start to narrow down. So even though you've increased the distance that the ray is traveling, the angle has also decreased. And so when can you see your shoes? Never. You can never see your shoes if everything is flat and vertical and horizontal floor. You can never see your shoes, which is kind of weird to think about, right? If I'm standing and looking in the mirror, surely I must be able to back up enough to see my shoes. That's not the case. Okay, you'll always see the exact same point on your body no matter how far back you go. So what is the difference between specular reflection and diffuse reflection? Well, it's pretty much this. If I look in this mirror, can you guys see me in that mirror? Yeah. There's my eyeball. Okay, you can see my eyeball right there. All right, that is what's called a specular reflection. You can make out my face in that image from the mirror. Diffuse reflection is if I do this. Okay, I fog up the mirror, and now, while it's foggy, you can't make out my face anymore. So specular is just that. It is a smooth surface. Diffuse is a bumpy surface. Okay, so if I think about a specular reflection, the mirror is nice and flat and smooth. All the rays that come in bounce off at a nice angle governed by the law of reflection. There are, of course, many rays that come in, and they all bounce off, obeying the law of reflection. But a bumpy surface has all these indentations or water droplets on it, like in the case of this mirror. And so when a ray comes in, it hits there, it's going to suffer the law of reflection at that point. The next ray that comes in will suffer the law of reflection at some other angle. And so all these incoming rays get scrambled into all these other directions, and that's why you can't make out an image in a diffuse reflecting mirror. Now, you're all familiar with this, right? You're all familiar with that problem. When you go to take a shower in the morning and you get out and go to your bathroom mirror and you need to shave or put on your makeup, right? You look in the bathroom mirror and you can't see yourself very well because it's all foggy, like that. Okay? How do you clean it off? You go like this. Right? You grab a washcloth, you take away all those water droplets, and now you make a nice smooth surface again. So here's a little beauty tip for you. That works fine, except it only lasts for about 30 seconds, right? If you take a washcloth and wipe off the mirror, 30 seconds later, it's full of moisture again, and there's all these water droplets all over, and you can't see yourself again. That's because you just took a hot shower. There was lots of water molecules floating around in the bathroom, and they're looking for a place to land. They're going to land everywhere, on the walls and on, other things in there. They're also going to land on the mirror, okay? But they don't like to land on things that are hot. That hot surface will bounce those water molecules back off of it. So if you wipe your bathroom mirror and it gets foggy again, the way to prevent that is to take your hairdryer and just heat it up for about 30 seconds. Wipe it, heat it up with the hairdryer for 30 seconds, and now it'll stay clear for the next few minutes. So you can finish applying your mascara. Sean, what kind of mascara do you use? Okay, this business of mirrors is kind of cool because, as you know, when you look in a mirror, your image is reversed. In fact, you're looking at me right now, and my image is reversed because in front of the camera, we have a mirror, okay? Right now, I'm holding up my right hand, but of course, to you, this looks like my left hand. Now I'm holding up my left hand. As you can see, that's my watch on my left hand and my ring. But of course, to you, it looks like my right hand. That's because mirrors flip left and right, okay? There's a great YouTube video about the flipping of mirrors, and it's by somebody called Physics Girl. She has a whole bunch of really great videos, physics videos. And she points out that it's not so much flipping left to right, it's flipping plus Z to minus Z. So take a look at that video, it's really good. When you think about light bouncing off of mirrors, it of course bounces at the angle that it came in at. Law of reflection says incident angle equals reflected angle. But what if we have two mirrors at right angles? Okay, so let's take a mirror, and let's take a second mirror and put it right next to the first, and we'll put them at right angles to each other. Okay, so we've made this nice sort of assortment of mirrors here. What happens when a ray comes in? A ray comes in and it bounces off the first surface. Okay, and we know that it bounces at the same as its incident angle, and so it's going to look something like that. When it bounces off the second mirror, it's going to bounce at an angle like so. And to make this really convenient, let's do the following. Let's say that this angle is 45 degrees. And if that angle is 45 degrees, then this angle is 45 degrees. Okay? And if those two angles are 45 degrees, then those two angles are also 45 degrees. Okay? Everything adds up. The outgoing ray is in fact parallel to the incoming ray. You might have seen these before, okay? They have these in dressing rooms. And the reason that they put these in dressing rooms sometimes, it's so that you can see your reflection the way other people see it. The bounce off the first mirror flips you from left to right. The bounce off the second mirror flips you back right to left. So if you stand in front of one of these mirrors and you raise your right hand, your image raises its right hand, okay? It's a very nice way to see what you look like, but there's a much more important feature here, which is the following. Let's say we didn't just do this in 2 dimensions. Let's say we did it in 3 dimensions. If you do it in 3 dimensions, it's called a corner cube, and let's see if we can draw it out. Okay, these are the mirror surfaces. And now any incoming ray will bounce 3 times and come out parallel. And this thing is called a corner cube. This last ray took a little funny jog there. Straighten that out a bit. Okay, it's called a corner cube. And it's used in physics quite a lot, but you are in fact familiar with this device, okay? I can guarantee you that at some point today, you have come across a corner cube in your regular daily life. Where have you seen one of these things? Where have you seen a corner cube at some point today? All right? Chime in. The answer is anywhere you see a reflector, like on a bike. Okay? A bike reflector has a whole bunch of little tiny corner cubes in it. All right? Why is that? Well, let's think about what happens. When you're driving in your car, here you are sitting in your car, okay, and you're looking out the front of your car. My car is looking a little backwards, but that's okay. Here you are. These are the headlights on your car, right here. When you're driving at night and somebody comes by on their bicycle, you would like to be able to see them. Okay, so here is the bike, person riding along, happy as can be. On the wheels of their bike, they have these little reflectors. And in that reflector are a whole bunch of these little tiny corner cubes. So, what's the point? The point is this. Light from your headlights will hit that reflector, and it will come back on itself. Almost exactly, a little bit off. When it comes back, it just skims over the hood of your car, past your headlights, and comes to your eyeball, okay? So that's the whole point of those bike reflectors. Take those headlights, send it back to the person driving the car, they can then see that it belongs to a bicycle. So it's kind of weird when you think about you're in your car, if somebody is in the car next to you and they have their headlights off, they can't see the bike reflector, okay? Only you can see the bike reflector because those headlights are coming straight back to you. They're not going to other people, they're coming straight back to you. So there's one more place where corner cubes are located. And this is very exciting, okay? They are located on the moon. Way back in the early 70s, the Apollo astronauts went up to the moon, right, when we went to the moon, and they brought a whole bunch of mirrors with them. They brought a whole bunch of corner cube reflectors, and they put them on the surface of the moon. And the idea was, we're going to use these someday for something important. And guess what? We are using them today for something important. We are taking these big lasers, just like these headlights, shining it at the mirrors on the moon and collecting the light that comes back down to us. And when we do that, we can determine very precisely the distance from the Earth to the moon. We know how fast light goes. We now know how long it takes in time to go there and back. And so you can measure the distance very precisely to the moon. And there was a talk recently about this. And the precision of that measurement currently is 0.8 millimeters. We know the distance from the Earth to the moon to within 0.8 millimeters, which is sort of remarkable when you think about it. Okay. All right, let's talk about spherical mirrors. And let's say a couple things and then I'll give you a clicker question. So mirrors, of course, don't have to be flat. They can be spherical. Okay, and you're all familiar with these. You have them on your car, of course. On the right passenger side of your car, that mirror is not flat, it's curved. And it says on the car door, you know, objects in mirror are closer than they appear. So when we think about mirrors, we can use the same idea of the law of reflection, but let's take a curved mirror. Okay, so a mirror curved like this is what's called a concave mirror. And light that comes in to this mirror will still bounce off according to the law of reflection, but it's the local angle that's important. So that ray will bounce off like so. But let's say we have another ray that's coming in near the bottom. It sees a different surface. It's going to bounce off like so. This is called a concave mirror because it's like a cave. You can crawl into it. Okay? And it has this interesting property that rays that come in parallel are suddenly focused towards each other. If the mirror is bent the other way, then it's called a convex mirror. And this is the one on your passenger side mirror of your car. And now a light ray that comes in near the top will be bent up at a big angle. A light ray that comes in near the bottom will be bent down at a big angle. Okay? So this is the primary difference between these things. Obviously, a convex mirror, if you just flip it around and it's reflective on the other side, it would behave just like a concave mirror. Okay? So it's really sort of the same element. It's just what side are you hitting? Are you hitting something that looks like a cave, or are you hitting something that is bent back the other way, called convex? All right, so let's think about our spherical mirror. There it is. It was made from some sort of spherical object, right? You cut it out with a big mill or something like that. There is therefore some center to this thing, right? If I have this radius r and I sweep it out, I'm going to mimic this arc of this spherical mirror. All right, what does this mean for the rays that are coming in? Well, when a ray comes in here, it is of course going to hit the mirror and bounce off at the exact same angle as it came in at. But that angle is relative to the local surface, and so we have to worry about this angle right here. This is your theta I. If that's your theta I, then this is your theta R. Okay? And so the ray takes off at that angle, theta R, and we know that those have to be exactly equal. So if those are equal, that means that it crosses this thing, which is called the optic axis, or the optical axis. It means that it crosses the axis at a very particular point. And that point is called the focal point of the mirror. Okay? Likewise, if a ray comes in on the other side, it is also going to go through the focal point. This F is called the focal point. There is a focal distance associated with that, which is this distance right here, F. And that F has a very special relationship to the radius of curvature of the mirror R, and it's the following. F is equal to R over 2. So what do we mean by focal point? Focal point means where all parallel rays incoming converge to? All these parallel rays that came in, bounced off the mirror, and they converge right at the focal point. Now, this sort of mirror is, of course, what you use in telescopes, right? If I think about a distant star looks like a point. It's so far away that the rays coming in from that star are all parallel. When they hit the mirror, I want them to go back to a single point. Put my CCD or film right there. That will generate a point, an image of that star. If the mirror behaves really well, right, then all those rays will converge at that point. But if the mirror is not quite perfect, if the mirror, in fact, is made from a sphere, not a parabola, then it suffers from something called spherical aberration. Spheres are really easy to make. Why are they easy to make? Because when you go to the machine shop, everything works on rotational principles, right? You go to the lathe, it has a big cutter on it that rotates in an arc. And so it's very easy to make circles. It's hard to make parabolas. And that's why typical astronomy telescopes, cheap astronomy telescopes, have spherical mirrors. Because a sphere is pretty close to a parabola until you get very far out to the edge. And when you get out far to the edge, then you suffer from something called spherical aberration. And in fact, you're all familiar with this idea of spherical aberration because that's what plagued the Hubble telescope initially. When they first built the Hubble telescope and they sent it up, you were very young, of course, but the pictures that came back from the Hubble telescope were totally blurry. All right? It was supposed to be nice, sharp pictures of stars, and they were just these blurry spots. And it's because they had spherical aberration in the Hubble telescope. A few years later, they went up with some corrective optics, literally a pair of eyeglasses to put on the Hubble, and they fixed the problem. And the Hubble vision went back to good 20/20 vision, and now it can see into the farthest reaches of the universe. So it's important to understand that spheres and parabolas are the same near the axis. They get worse as it goes farther out. So let's draw an optic axis. And let's put our spherical mirror right there. And now let's take an object, and we'll put the object right there. The spherical mirror, of course, has a focal point. If the center is there for the spherical mirror, then the focal point is somewhere around there. We'll label that F. When we think about the rays coming off of our object, we know that rays come off in all directions, but there's a few that we're very interested in. One of those is the following. There will be a ray of light from the object that goes parallel to the optical axis. Okay, it's going to come towards the mirror parallel. When it bounces off the mirror, it's going to go through the focal point. Okay, and it'll just keep going on out. All right, so that's a very important one. The second one is rays going through that focus are going to come out parallel. Okay. And there's one more point, which is the following. If the center is there, then rays that come through the center just keep going, bounce off the mirror, and come back on themselves. Okay. Let's label those three rays. This is ray number 1. This is ray number 2. And this is ray number 3. And let's see if we can identify the rules that we just wrote down for those 3 rays. So ray number 1 is the following. Parallel ray goes through the focus. Okay, and that's exactly what we drew. There was a ray that came in parallel, it bounced off the mirror, and it went through the focus. What about number 2? Number 2 is really just number 1 in reverse. Rays through the focus go parallel. All right, number 2 was this one that came right here. It went through the focal point, bounced off the mirror, and then went parallel back. And the final rule is this ray number 3. Rays through the center do not bend. Okay, this is image formation. And these 3 rules are important to understand because they not only apply to mirrors, they are going to apply to lenses once we start talking about lenses. So, where is the image in this picture? The image is where the rays all meet. They started there at the tip of the object, they went out in all these different directions, and then they came back together right there. So that's where the tip of the object is. The base of the object is on the optic axis. Okay? So this is a nice way to draw it. When you draw the object and you put it on the base of the optic axis, its image still has its base on the optic axis. And so all you really need to figure out is where's the tip of the image. Okay? And so this is the final point. Image is where they meet. Now, when we have image formation like this, you have to classify it as either a real image or an imaginary image, a virtual image. Images are real when real rays meet up. Okay? In other words, could I put a piece of paper there and form an image on it because real rays are coming to meet up with it? Yes, those 3 converging rays all meet right there. Virtual image is when the dashed line rays meet up. And that means you can't form that image on a piece of paper. So when we were doing the flat mirror, we said, where's the image? It's on the other side. But remember those dashed lines that went to form that image? That means it's a virtual image. There's no real light that got there. All the real light stayed on this side of the mirror. In this case, there is real light that went to form the tip of that image. Posted, it said the following: an object is placed 2 meters away from a concave mirror of focal length 1 meter. So, mirror to focus is 1 meter, but the object is placed 2 meters away, which is interesting. That would put us right at the position C. Right? Remember, F is half of the radius of curvature. C is the full radius of curvature. So that's where the object would be. Where is the image? Okay? And is it bigger, smaller, real, virtual? Let's see if we can follow our lens rules and figure out exactly where it should be. All right, rule number 1. Parallel rays go through the focus. Okay, here comes a parallel ray, goes through the focus. Okay, Rule number 2, rays through the focus go parallel. All right. And rule number 3 is rays through the center don't bend. Well, I guess a ray through the center would be straight down on itself. That would be ray number 3. So let's label those and make sure everybody's on the same page. This is ray number 1, this is ray number 2, and this is ray number 3. And now where is the image? It's where they meet. That's where they meet. The image looks to be exactly the same size as the object. Here's our object, here's our image. Okay? So it's also real because there are real rays coming to form it. And it is inverted, which just means upside down. And so the answer is C, of course, real and same size. Okay, excellent, excellent question. Okay, let's talk about something called the mirror equation. And this is the mathematical tools for figuring out exactly where that image is going to lie. So let's draw our picture again. And this is our mirror. At a focus about there. And when we have an object, we know that it's going to form some image somewhere. We're not exactly sure where yet, but this thing is our object. This is our image. There are some distances that we can measure here. One of them is this. Distance to the image. From the mirror, from the apex of the mirror to the image, what is that distance? Likewise, we can measure the distance to the object. Okay, from the apex of the mirror to the object, what is that distance? And then finally, we can, of course, measure the focal length, which is from there to there. So the mirror equation allows us to determine where that image is going to be located. And the mirror equation is the following. One over dO plus 1 over di equals 1 over f. And remember that f was equal to r over 2. Okay? This thing is going to help you determine where di is. So let's take a look at the last clicker question that we just looked at and verify that this equation is in agreement with that. In that equation, we had the following. We had that the focal length was 1 meter. But we also had that DO was 2 meters. Can we solve this now for DI? Well, yeah, that doesn't look too bad, right? Let's take this equation and let's solve it for DI. All right, so we've got 1 over dO plus 1 over di equals 1 over f. So let's move the dO to the other side. I got 1 over di equals 1 over f minus 1 over dO. And now I know all those numbers, so we can just plug them in. 1 over di equals 1 over f, which is 1 over 1, minus 1 over dO, which is 1 over 2. All right, 1 minus a half is a half. So 1 over di is equal to a half, and if I flip it back over, I get di is equal to 2. And that's exactly what we found on that picture a second ago. If the object was 2 meters from the spherical mirror, then the image was also 2 meters from the spherical mirror. In this mirror equation, all these numbers are positive if they are to the left of the mirror. So DO measured to the left is a positive number. DI measured to the left is a positive number. F measured to the left is a positive number. If you solve the equations and you end up with a negative sign for DI, that means the image is on the other side of the mirror. It's on the right side of the mirror. Okay? And that'll happen when you start to get very close to the mirror. If we have an optic axis here and we have a plane mirror, then we know that an object will have a length DO, but its image is on the right side. And it's to the right, and therefore DI is negative DO. And so now if you go back to your equation, right, we had 1 over DO plus 1 over DI equals 1 over F. We're going to have 1 over DO minus 1 over DO equals 1 over F. And if 0 equals 1 over F, the only option is F is equal to infinity. Remember that focal length is related to radius of curvature, and so you're really asking the question, what is the radius of curvature of a flat mirror? In other words, what saw would cut out a flat mirror? A saw that had a radius that was infinity. Okay? So when we saw the image being formed, it looked like it was smaller or as big as the object. Can it in fact be bigger? And the answer is yes. And so we can quantify the magnification. The magnification M is just related to the height of the image over the height of the object. And that is directly related to how far away the image is versus how far away the object is. So in the last example, when we had the object placed right at C, the image was also at C, but it was inverted. -2 over 2 just means magnification of 1, but an inverted image. So if the magnification is less than 0, if it's a negative number, that just means the image is upside down, it's inverted. All right, let's talk about convex mirrors. Right now, we just covered concave mirrors, but of course you can have image formation with convex mirrors. Let's see how that works. Okay, so here's our convex mirror, and let's draw the center of it, which is about there, and let's draw the focal position, which is about there. Notice the focus is over here on the right side of the mirror now, which means it's a negative number. So if I put my object right there, how do I find the rays that are going to form the image? We do the same thing that we did before. We follow those 3 rules, except we have to remember that the focus is over here and the center is right there. So this says that rays that are parallel to the optic axis, are going to go through the focus. But this thing is a mirror, right? It's a convex mirror. So there's no real light ray that penetrates through the mirror. It becomes a dashed line. Okay, this was rule number 1. All right, if it's a dashed line, what that means is when you look at this mirror, it's going to look like it came from there. All right? What about rule number 2? Rule number 2 was rays through the focus go parallel. All right, there's the focus. How do I get to it? I go like this. I get to the mirror, and it stops becoming a real ray. It, in fact, becomes a virtual ray. And this is ray 2. I guess this one here is fine. Okay. That one looks good. Ray 3 is going to be the hard one to draw. Okay. And before we do that, let's talk about ray 2. Ray 2 bounced off and went there. Okay, so it looks like it came from there. And then ray 3 is the one that goes through the center. And if I go towards the center, off it goes. That's ray number 3. And now this is a little hard to see, but hopefully you can see that those 3 virtual rays all look like they are intercepting each other right there. Okay. Book might have a better picture of that. Sometimes it's a little hard to see up here on the screen exactly where it's intercepting, but that should be about the right position. This is, of course, a virtual image because there's no real rays that are forming it. It is also demagnified because it's smaller than the object. And this is what they mean by the passenger side mirror. Objects in the mirror are closer than they appear because it looks kind of small, right? And there's that great scene in Jurassic Park where he's looking in the rearview mirror at T-Rex, and it says objects in the mirror may be bigger than they appear. Okay, and it is also upright as opposed to inverted. That's how you would describe it. This sort of mirror also obeys the mirror equation, as long as you remember that stuff on the right side has a negative sign, stuff on the left side has a positive sign.